So this is somewhat of a review, but we're going to be talking about radiation interactions in units of measure. And bear with me here because they've kind of changed my my controls here a little bit, and that screen is a little bit different from the screen that y'all have. So here's our objectives. We're going to talk about relationships between radiant energy and the site of interaction, which is going to be important. We'll talk just a little bit more about early deterministic effects, as well as late deterministic effects and stochastic effects. We're going to differentiate with the different kinds of quantities and identify the appropriate symbol for each quantity. The big takeaway, the big thing that we're driving at today is to be able to calculate an effective dose, and then having calculated an effective dose, be able to project out a collective effective dose, which is the way that the NCRP arrives at many of their dose limitation recommendations as well as public exposures to radiation. So this may be helpful, and it's something that we've not. This would be a review of physics here, but these are the various energy ranges, as well as the types of interactions we would expect to see at those energy ranges. And so at like 1 to 50 keV, most of what we have is coherent scatter and photoelectric effect. Once we get into the range of 60 to 90 keV, photoelectric starts to fall off and Compton starts to predominate. From 90 to 200 and even beyond that, we have pretty much the complete domination of Compton effect, just scatter, all the way up to 2 mega electron volts. So like we've talked about in CT, this range of energies right here tends to be the diagnostic range of energies for X-ray, because within that range of energies is where we have photoelectric effect predominating. Occasionally we go above 90 keV, but not much higher than 120 keV or kilovolt peak, right? For our diagnostic exams, because beyond that we just have scatter. It does not give us anything other than noise. It's almost like those. I don't know if you've ever been between the dial on radio stations. This would be between the dial, like that range of energies that photoelectric is in is when we have the station tuned in. Anything other than that is just static. Until we get to about this range of 1.022 mega electron volts to 10 mega electron volts, we could have pair production. So it begins at 1.022 mega electron volts, and it continues up to 10 mega electron volts. Above 10 mega electron volts, we can have photodisintegration. There's not many of us who are playing with that apart from the therapists in the room. They occasionally can cause photodisintegration. Pair production is a big part of nuclear medicine, particularly PET examinations. So knowing that we have these different types of physical interactions that occur with different photon characteristics, different energy levels, we also have different types of biological effects that can occur. So basically our area of study is it has three foundational ways of thinking about it. There's the physics, so these photon interactions. There's biology, right? And then there's chemical stuff. We're waiting on the chemical stuff, but today we'll be talking about physics and biology quite a bit. So what we know from the way that these different types of energies interact with the body is we have these different classifications of effects that occur. There's things that can occur very acutely given the size of the dose, and we're going to call those early deterministic effects. They happen soon after receiving the radiation. If the radiation is sufficient enough, if it's a large enough dose, like 2 gray to the whole body or higher, we can see things like nausea, fatigue, vomiting, skin burns, loss of hair, which might also be called epilation, GI disorders, fever, blood disorders like white blood cell counts can drop off, and infection can set in, or anemia, and then sloughing off of that outer layer of the skin. Okay, those are pretty severe, and they happen very soon. So they're the amount and the amount of these things and the significance, like the severity of them, is determined by the dose. So we call them deterministic or early deterministic effects. Related to that is what we would call late deterministic effects. And so these are also determined by the dose, but it takes them some time before they manifest. Probably the big one, the one that has the most controversy around it, is cataractogenesis or cataract formation. That is determined by the dose, but it has a threshold. So it has some funny things about it. But things like fibrosis and organ atrophy are determined solely by the dose without threshold. And in fact, the fibrosis was the reason for why the early radiation workers had to have the amputations of their fingers and things like that, is because of the scarring and things caused by the radiation. We do see some of that in radiation therapy. Of course, reduced fertility and sterility are also late deterministic somatic effects. Even though those are germ cells, right, the organ systems themselves, the reproductive organ systems, are still made up out of somatic cells. So that's worth pointing out, that when we're talking about these, we could just call them early deterministic effects or late deterministic effects. The somatic, that word is referring to the soma, or the cells of the body, right? So it's just further telling us this is talking about cells of the body, cells that make up the body, not reproductive cells. Okay? So when we talk about reduced fertility or sterility of the cells of the body, we're talking about damage to those reproductive organs, right? A lot of what we know about this stuff comes from a lot of very unethical experiments that were done, right? Both by U.S. scientists and also by Nazi scientists. What we know about the effects of radiation on fertility and sterility comes from the Nazis, and experiments that they did on Jewish people. These experiments will never be repeated, right? So they're not experiments that we're continuing to explore. And so what that means is we have kind of ballparks for a lot of these. Numbers can be really inaccurate. We have general ranges that we'll be working with, just because of the ethics that surrounds this issue. The stochastic effects, I've said, are like the coin toss type things, and that's cancer and the hereditary stuff. So when we say hereditary or genetic, we are talking about these things impact germ cells, right? The ways that germ cells can cause reproduction and things like that. So that is slightly different from damage to the reproductive system. Does that make sense? I'm not trying to split hairs, but you'll notice all stochastic effects are late in nature. The soonest one that can manifest would be leukemia, and it happens 2 years after exposure. So the stochastic effects require a good amount of time before they manifest. Okay, I'm going to skip over this. The big thing here, though, is what we know about radiation and its effect on the cells, and what we know about biology in general comes out of what we know about radiation. So Wilhelm Röntgen did his experiments in 1895, right? And the way that I remember that year, 1895, is because of Rankin's wife, who was probably the first person to really blow the whistle and say, hey, this stuff's potentially not safe. Because she said when she saw that radiograph that I have seen my own death, right? So the way that I remember 1895 is like that Columbus mnemonic, that in 1895, Miss Rankin was glad to still be alive, right? It's just silly mnemonic. Henri Becquerel did his experiment the next year, within just a few months of Rankin's experiment, and discovered that uranium salts could cause similar exposure to photographic plates. And we start to see the beginning of people questioning, okay, what this stuff, the power that it has, is it completely safe? Clarence Dally, Thomas Edison's lab co-partner, one of his best friends, is the first documented radiation fatality. And there were definitely probably radiation fatalities prior to this, but he's the first one that we have, on the record books in 1904. And so that's just less than a decade after the discovery, we have the first fatality. Even prior to that, though, Dr. Miran Kasabian, who was, I think, a dentist, if I remember right, working with X-ray equipment a whole lot, and these would have been unshielded tubes. He documented the amputations that he suffered due to early deterministic effects, right? So skin burns, as well as the fibrosis to the skin, which caused damage to the capillaries, which caused necrosis, which mean they had to amputate his fingers. He died shortly after documenting it, and was also another early whistleblower saying this stuff is not safe, but pay attention to what we're doing, and maybe there's some safe ways we can handle this. In 1919, a scientist at Baylor, Mueller, and if you notice, that is an X-ray tube that he has right out there in front of him. And below that is a magnifying device. He's irradiating fruit flies, because fruit flies are very genetically similar to the human chromosome. And so he was able to document the mutations that were occurring within these fruit fly populations. So the Dally and Kasabian both documented those deterministic effects. Mueller is now saying, yes, there's also genetic effects that occur as well. There's also reproductive things that are heritable, hereditary defects that can occur. He also proved that we're not going to make Godzilla doing this. All of the hereditary effects that are caused by radiation also can occur from natural causes. And the reason for that is radiation is natural. It's part of the environment. What we are seeing, though, is an increase in its use for artificial reasons, like for power or for medicine. But we're not going to make Godzilla or the Teenage Mutant Ninja Turtles. That's basically what his experiments told us. But at the same time, they also said that, yes, this can cause genetic damage. But here's a question to think about. Knowing what we know about these different kinds of responses that can occur, whether deterministic or reproductive in nature, as well as different types of the physics of different types of radiation energies, how do we measure the different kinds of biological reactions seen after radiation exposure? Because what we've just talked about is a broad spectrum of reactions. So what are some ways that we could measure that? So I don't anticipate the measures will change that much over the course of our lifetime. They changed a lot, though, in those first 100 years. So let's look at some of those changes real quick. The ways that we investigated it was we developed a number of, so the medical community was the first to be alarmed by the number of injuries that were being reported, and they created the British X-ray and Radiation Protection Committee. So this is not a council, this is not a policy-making body. These were just scientists who are asking those kinds of questions. How do we measure this stuff, as well as classify the responses? They were handicapped by the fact that they were not policymakers, they were just doing research. They were able to eventually arrive at something like a unit of measure, but we no longer really use it all that much. But I think they did eventually propose the Rankine as a unit of measure of exposure. But probably the most popular unit of measure in that early time was the skin erythema dose. Completely unreliable, completely inexact, because it would differ from person to person, as well as the ethical problems of just saying, yeah, I think I've had enough, it's time for me to go home today because my hands are burning, right? And your manager saying, no, your hands aren't burning more than Clark's hands, so get back in there and get back to work, right? I doubt that was a conversation anyone ever had. But what I am talking about when I talk about these ethical issues is the somatic damage that would result from repeated erythema. If you met your erythema dose over and over and over again, eventually you're going to have these kinds of burns on your hands. And so these documents, this was taken in 1936, and this would be an X-ray worker. This was an X-ray tech's hands. And the burns that they received from working with the X-ray tube that was unshielded. So radiodermatitis, those would be the early somatic damage. On your slide, the cancer and blood disorders, put a bracket around that. That is, those are going to be stochastic in nature. The radiodermatitis would be deterministic in nature, right? So I want us to be able to start to differentiate those, even though we're going to see them in lists together. I want to make sure that if you see a list of terms related to radiation exposure, that you're able to parse out, okay, that's a deterministic effect and that's a stochastic effect. So radiodermatitis, deterministic, determined on the amount of dose. The cancer and blood disorders would be stochastic or random in nature. So we have First International Congress of Radiology, 1925. The ICRU was formed also the same year. And the ICRU was charged to define the Rankine. And they eventually developed the International X-ray and Radiation Protection Committee, which evolved into the ICRP, the International Commission on Radiologic Protection. So they were the first to scientifically define a unit of exposure, at least, to radiation. And out of that unit of exposure, so since we can now develop things like Geiger counters or ways to measure what these photons are doing physically in the air, they could come up with what they called a tolerance dose or a threshold dose. Now I want to point out this is not a way that we continue to think about things. So this is different from a dose limit. They're saying that it's okay if you get this much, right? Like it's perfectly fine. And there are still some people in the physics world who think this way. That's why I want to point that out. There are health physicists who work in hospitals who have embraced the philosophy of the tolerance dose. That this amount of radiation is perfectly fine. We could all have this amount of radiation all day of every day of our life and we'd all be fine, right? So there are intelligent people who embrace this stance. This is not the stance that we embrace as imaging technologists and therapists. Okay? So I'm not trying to set up as being at odds with the people who are doing, the standardization and testing for our equipment, but you occasionally will hear people say that, and you maybe have to gently remind them, yes, but here in X-ray we don't work off of a tolerance dose. We work off the dose limitation, which is a total opposite. Limitation means there's a maximum amount, and we want to stay way below that. Well below that. But tolerance developed enough steam, and it was used for radiation protection purposes pretty much until the 1950s, maybe even beyond that. And so they came up with some recommended tolerance limits and things like that. You know, if you went beyond that, this amount daily, you know, watch out. They actually dropped it within a year of establishing a tolerance dose. They dropped it in half because they were continuing to see people with burns, and the cancer started to show up. So, the only thing I want to point out in addition to that about these tolerance levels is they recognized that they needed a better unit than just a unit of exposure to radiation, and they also needed a way to capture what's going on in terms of the late stochastic stuff, the random stuff that's starting to show up. Right? Like I said, it would take 20 years before we would see something like the leukemia. We're starting to see it now in 1930-something. How do we control for that? The game changer is August 6th and 9th of 1942 with the use of nuclear weapons by the United States government on Japan. When the whole world saw the power that was there latent in the atom, all of a sudden, immediately following that, we have the first radiation protection measures. So tolerance dose gets thrown out the window immediately after that. And we recognize that we need to have ways to quantify human exposure, and also not just the exposure itself, but also quantify what it's doing biologically. So we have the first radiation signs. The industry and hospitals now start using things like Geiger-Muller counters and film badges, and they become fairly widespread. The tolerance dose more or less evolves into what we would call a maximum permissible dose, and so this is a slight shift, right? From tolerance, like anyone can tolerate this amount, it's okay, it's fine, to setting a limitation, like no one should get more than this, right? And so they have the MPD, or the maximum permissible dose, evolved sometime in the 1950s, so shortly after the use of the nuclear weapons. And the R has continued, the ranking has continued to be redefined. So we really struggled with how do we measure this stuff and quantify the amounts as well as the biological damage. Dose limits, the first time that we see dose limitations in the 1970s. And what we were trying to determine is beneath this amount, we can consider things safe. And by quote-unquote safe, I mean, it's important that safe is in quotes. What we're saying is that it's impossible for us scientifically to differentiate between the effects that this exposure to radiation might cause versus the effects of that canned Lysol that you used for cleaning up your kitchen, or the fact that you put gas in your car today, or the exposure to carcinogens that you received while you were jogging down the side of the road, right? So they wanted to keep it below any other LD 5030 of anything else that's out there that could cause damage, right? Like mercury in fluorescent lights or in these computer screens. All of these different chemical exposures that we receive from everything that we do here in modern times. So the big takeaway, though, for this is that both the ICRU and the NCRP adopted SI units in the 1980s. And this was an important shift. Honestly, it's a shift that we've not completely made yet. Even though we did this in the 1980s, we still continue to see things placed in traditional units. and so we still have to do some conversions. But the SI units that we're going to look at today, I think, are the most helpful for describing what radiation's doing. So here's an overview of what these units of measure are. In the SI system, exposure is coulombs per kilogram, and I want to stress that it is a that measurement has to be done in a lab environment because it's very specifically defined. We'll look at the definition a little bit in just a second. But it's almost like the atomic clock. Like its measurement of second is very precisely defined as like the movements of a hydrogen atom or something inside of a very specific container at a very specific place in the Earth's atmosphere. Exposure for the coulombs per kilogram is very similar. But it is measuring ionization of air within a container. But from it we are able to extrapolate and take the air kerma. And kerma is an abbreviation for kinetic energy in matter. So kinetic energy released in matter. And the SI unit for that is a gray in air. So for most of our purposes, we're going to use the gray in air as the measurement of exposure. And the reason for that is it allows us to be a little bit more loose in our definitions. We don't have to worry about scientifically perfect setups because what we're working with is in the hospital. It's not some perfectly defined unit of air somewhere. It's like hospital rooms and patients who are being exposed to radiation. So we will use the air kerma mostly. There has been some modifications in the kerma, and there's people proposing slightly different measures there, but those have not yet become popularized. Absorbed dose will be the gray in tissue, so the gray sub T. I don't know why it says air kerma there. That's kind of confusing. I would just keep that as absorbed dose and X out that additional air kerma. And then finally, to move from the gray to the sievert, we're going to weight the radiation. And if we weight just the radiation, that's an equivalent dose. It will be expressed in sievert. If we weight both the radiation and the tissue, then we have an effective dose, and that's also expressed in sievert. I want to point out the nice thing about this SI unit system, just a sec, is all of these are the same special unit. Does anyone know what that unit is? It's joules, which is the unit of work. Joules per kilogram. They all mean exactly the same thing. So I'll say that again. It's a special unit within the SI system of work done per kilogram of something, right? The only thing that changes from unit to unit is what that kilogram of something is. When we're just talking about exposure, it's a kilogram of air. When we start to talk about effective dose or how it's absorbed in tissue, it's a kilogram of tissue. When we start to talk about how the radiation was weighted, we weight the radiation for that kilogram of tissue. And when we start to talk about an effective dose, we get really nitty-gritty and we say a kilogram of kidney versus a kilogram of ureter versus a kilogram of muscle versus a kilogram of bone, right? So that special unit does a whole lot of work. And we've given it different names to indicate what kind of work we're talking about. And that is the reason why if we ask a health physicist what was the patient's dose, they'll look at it as kind of funny because they recognize the unit is the same throughout, but what the expression is important. So here's just a way of looking at different types of radiation quantities and how these would have been treated in the traditional system. Because with some of these documents, we will have to still think about the traditional units of measure. If I see something in rank and it's talking about exposure, okay, If I see something in rad, that's absorbed dose. And then the rim would express both equivalent dose and effective dose. In fact, some of your dose reports that you receive from the hospital will probably be in rim or millirim or something like that. Here's just the SI units currently being used. Okay, so let's get down to the nitty-gritty with what exactly this exposure thing is. It's the total electrical charge. So coulombs are a measure of charge, right? The total charge of one sign, either all pluses or all minuses, so we can either measure, we can look at either side of the ion pair that's produced through ionization. We can look at the positively charged atoms that are produced or the negatively charged electrons that are produced. It doesn't matter. But we're going to either look at all positives or all negatives within the device. That either X-ray, gamma ray, alpha particles, whatever is interacting with energies up to 3 million electron volts generate in dry, non-humid air at standard temperatures, of 22 degrees Celsius at a pressure equivalent to sea level. So it is the amount of energy produced up to a certain amount in non-humid air at sea level. So as you can imagine, that doesn't describe any hospital room I've ever been in ever, right? So this is a very, very helpful unit. It's very, very scientifically exact. But anytime I'm measuring in coulombs per kilogram, I would need to be in a very controlled environment to make these measurements, right? Where do we have that controlled environment? Well, inside of a Geiger-Müller tube, for one. We can pressurize the inside of an ionization chamber. We can make sure that there's no humidity inside that ionization chamber. We can control things within our instrument to make this controlled thing, but it's not going to help me for like my film badge, right, or my OSL. It's definitely not going to help me for making an X-ray exposure to the patient or nuclear medicine calculation or scintillation, what have you, right? But it does give us a very, very exact base level measurement, and it gives us a way to quantify radiation exposure. It's very, very precise. Away from a laboratory, we are going to use very, very small and less complicated instruments to make the measurements, so like the ion chamber or the Geiger-Müller counter. And we're going to have to send off our Geiger-Müller counters and stuff back to the lab to be recalibrated. I think it's once every 13 months or something like that. So here is an example of what that device would look like that can make the measurements. And it's going to be important for us to think about this. So this is a cube here. And what we're going to do in this instance is we're going to have controlled what gases are inside of this cube, right? And as the X-ray beam passes through the cube, it causes ionization within that measured volume of gases. And then we have a collecting plate, and in this case what we have is we're collecting electrons. So the collecting plate is positively charged because we want to attract the electrons towards the collecting plate. We've negatively charged a plate opposite it to force the electrons towards the collecting plate, right? And then every electron that we capture represents an ionization. So we can quantify how many ionizations occurred. And we're talking about millions, trillions of ionizations would occur. A whole lot. But that is the basic idea of how ionization chambers work. Here again is that unit. And the Coulombs is the basic unit of electrical charge. And the SI unit is, it equals 1 Coulomb is 1 electrical charge produced in a kilogram of dry air by ionizing radiation. We'll talk about conversion here in a little bit. So if we're converting from Rankine to coulombs per kilogram, the number to remember is 2.58, and that will allow us to convert from Rankines to coulombs per kilogram. The question might be like, why do we have this like 2.58 times 10 to the negative fourth? That is simply how it's defined charge versus the way the Rankines define the charge. This is probably the most difficult conversion that we have to do. So we'll look at that here later on with an activity. Okay, moving along, the air kerma is going to be a much more practical unit of measure for us. So coulombs per kilogram, that happens in a lab environment. We might send our Geiger counter off to the lab every year or so to have them look at that. The air kerma is something that we can then apply once we have that Geiger counter accounted for, that ion chamber's been calibrated. We can now look at air kerma regularly, and the acronym might mean kinetic energy released in matter, sometimes kinetic energy released in material. There's some debate about what exactly the acronym means, but I just say kinetic energy released in matter. So let me zoom that out. And again, I said the way that this will be expressed is going to be gray sub A, and it equals a joule per kilogram. Now, another way that can also be written is joule times kilogram to the negative 1. That's just a fancy scientific way of writing the exact same thing. Okay? Some folks will use that. Can y'all see that slide okay? My setup looks a little bit different from y'all's. So it might be written joules per kilogram to the negative 1. And here's just another discussion, a little bit more discussion of that. Knowing the air kerma, we can calculate a dose area product, and I predict that this is going to become increasingly more common. Most of the digital radiography equipment that you use, the Nuke Med, CT, has some way of calculating a dose area product. And so it's the sum of the air kerma over the exposed area, right? And it's going to be specified in units of milligray per centimeter squared. So all it's done is it's just said, okay, over this volume of tissue, here was the exposure that occurred. This is actually very helpful to have, particularly if it's something that's read out immediately after the exposure is made. I imagine this is going to become increasingly part of standardization. When we talk about absorbed dose, this is now gray in tissue, and it's the quantity of energy per unit mass absorbed by the irradiated object. We're still going to think about it as joules per kilogram. And it's going to be important to think about, as we think about dose, the skin being at the surface of the body is going to receive the majority of the dose for all radiation therapy and X-ray exposures. With nuclear medicine, dose gets a little bit more difficult to track down and quantify. But as the radiation penetrates deeper and deeper into the matter, we will have equal amounts of drop-off in dose because it's losing its energy as it penetrates the object. Part of how that works is it's dependent on the atomic number of the tissue that's within the area of exposure, particularly its Z number. So within the diagnostic range of energies, even though we like photoelectric effect, that does still represent ionization of radiation within the body. And so we see more ionization within the bones than within soft tissue. Once we get to the higher levels of energy, like things over the 1.022 mega electron volts, we start to see sometimes what we call like a Bragg peak, or a point at which energy deposition increases exponentially and then falls off. We'll talk about that some more on a later day. So, and here's just a way to convert between rad and gray. But whether it's talking about rad or sieverts or what have you, rim to sievert or rad to gray, I just always remember 1 rad equals 1 centigray, and that lets me do all those conversions because they are all the same unit. Okay. We are going to need to be really comfortable with moving zeros around because we're going to see some big numbers and small numbers and have to move between them pretty fluidly. This is the way I tend to remember how things are done because, like I've said, if I remember this, all the rest of it I can figure out. So it's kind of a nice one-stop shop for conversions for most all the conversions that, and say I never even remember the coulombs per kilogram, chances are I'll be just fine because if I remember that, I've done the predominance of types of conversions I need to do. Okay, I feel like this one's a little bit confusing because when we talk about SID in X-ray, we mean something, and honestly, therapists, when they talk about SID, they mean something different. So here's yet another SID that means something else entirely, but it is a surface integral dose. I prefer dose area product, but they are talking about surface integral doses now. And this is the total amount of radiant energy transferred by ionized radiation to the body during an exposure, and it's particularly the skin. This slide got a little messed up. So we've talked about this to some degree, and we will be coming back to this again. But when we talk about the different sources of radiation, different types of radiation, whether it's particulate or electromagnetic, we have to account for that with a quality factor. So each one of these numbers here are the weighting factor for the radiation exposure. And that's written as W sub R. And the helpful thing with this is photons, beta particles, gamma photons, and those all have a weighting factor of 1. Neutrons have a weighting factor of 5. But the fast neutrons and alpha particles, as well as the weird subatomic things, they all have a weighting factor of 20. That means that they have a much bigger impact on biological systems. And if we were to ask why is that the case, this concept of linear energy transfer, or LET, will help us understand that better. This is the amount of energy transferred by an incident radiation per length, right? So the amount of ionizations that occur over a length, and we express it in kiloelectron volts per micron. Kiloelectron volts per micron. Radiation with a high LET transfers a large amount of energy into a small area and therefore can do more biological damage than a low LET energy radiation. That's why we have these different weighting factors. The point of confusion that most students run up against is the amount of penetrability. The particulate radiations that have a high LET do not penetrate as deeply. So alpha particles would not be able to get through your clothing. but they're going to give off a whole lot of energy while they're moving through the clothing, and that's why they're considered high lead, is they're giving off all that energy very quickly. They're not able to travel as far. Versus X-rays and gamma rays, they have a low lead. They might pass straight through your body without a single ionization occurring. So they have a low lead, but their penetrability is that much higher because of it. So here is that illustrated, just kind of graphically, the path of an electron. You can see it's bouncing around, right? And the LET is measuring how much energy is deposited as it moves through different depths of tissue. And eventually it stops. And it's just helpful to see. What we're talking about too is every time it ionizes, it's probably scattering in a different direction as well. So it's fairly imperfect. But that is what we're considering when we talk about a radiation weighting factor. And this is how we determine an equivalent dose. So this EQD. I want to stress that it's a dimensionless factor. It's just a factor, which is an algebraic term, right? It's just a way of multiplying things. It does not mean anything in itself. It doesn't have a unit. But it just allows us to place the different biological reactions that occur due to different degrees of LET on a scale and set them in equivalence with each other. So here again is that information just kind of repeated for LETs at different energies. And the way that we're going to calculate an equivalent dose is we'll multiply the absorbed dose times the radiation weighting factor. Okay? And this is expressed in a sievert. So if we see something in REM, we can immediately think sievert and just do our quick conversion between the two. Here's I think this comes from the textbook that I've excerpted here. It's just showing you different types of calculations for that. It may just be helpful for when we're doing the math later on. So if we want to consider the effects of radiation on different types of organs and tissues, we're going to think about whether the organ has a potential to be damaged or whether the radiation also could cause the organ to become carcinogenic, whether it could produce cancer within the organ. So they have looked at a whole lot of data, largely from atomic bomb survivors and as well as from Chernobyl. And they've churned out all this data, and they've made some basic evaluations of how these different radiation exposure amounts led to different types of either deterministic or stochastic effects, and those were weighted across all the organ systems of the body. So this is just an example. I want to point out to you that anytime you're asked to calculate an equivalent, an effective dose, I'm not asking you to memorize weighting factors for all the tissues of the body, because they differ based on radiation type and energy level, etc. So I will tell you what the weighting factor is for the tissue, right? I will not tell you the weighting factor for the radiation because it's pretty easy to remember. It's just either a 1 for all the photon stuff, 5 for neutrons, and then 20 for alpha particles, and you're done. So that's an easy one. This is big books that the dosimetrists have and computer programs that have to crunch all of these numbers. No one would ever memorize all of this. So you do not need to memorize this. The only reason I include this information here is it shows you how those weighting factors are broken down and how they represent significance of different areas of the body. And all of this is used to express an effective dose. It provides a measure of the overall risk of exposure to ionizing radiation. NCRP report number 116 defines it as the sum of weighted equivalent doses for all irradiated tissues or organs. And so the way it's calculated is indicated here below as the effective dose equals the absorbed dose times the radiation weighting factor times the tissue weighting factor. So you can see here's an example of a problem. We're given an area of the body and a weighting factor for the tissue, as well as the absorbed dose in gray. What is the effective dose? And so we have to multiply that dose of 0.5 gray times the weighting factor for the radiation times the weighting factor for the tissue, and that gives us an approximation of what the dose was for, in this case, the lungs. And typically this is expressed in millisieverts for dose limitation purposes. Sievert's pretty big unit. It's a repeat. Okay. Here's just an example of how these things may be distributed across the body during radiation exposure with what is it saying? AP lumbar spine. And so the skin, you're going to see on the anterior surface is going to receive the majority of the exposure. And then the bone marrow, if there were a fetus within that area, it would receive another significant dose. So the effective dose can be calculated at 3.13 millisieverts. Once we have that effective dose for various exposures, whether it's to radon gas or medical imaging or living next to a nuclear power plant or any of the other ways that people might be exposed to radiation, we can extrapolate that across an entire population. And this is helpful for us to make determinations of risk as well as trying to figure out how these different exposures are going to affect the population as a whole. And so that's what we're talking about when we talk about a collective effective dose. Okay? The unit for this is the person's sievert, and it's the average effective dose for any individual belonging to a certain population group. So we would define the population group as, for example, everyone living in the United States of America, or everyone living within like Belarus, Ukraine, and anywhere else that Chernobyl was impacting. Anyone living within 50 miles of 3 Mile Island, right? So we would have to have the population number because we're going to divide the average exposure. We're going to figure out an average exposure across that entire population. So here's an example of the kind of problem that we might be asked with this. If 200 people receive an average effective dose of 0.25 sieverts, the collective effective dose would be 200 times 0.25. It's 50 person sieverts, right? So the important thing here is that as the population size grows, even if the dose remains the same as the population size grows, we see an increasing number of significance, right? So if this population that received this average dose of 0.25 grew to 10,000 people, it would be that much more significant because as that population responds as a whole, we could see an increased incidence of genetic mutation. And they're going to be able to share those genetic mutations. So if you're wondering how on earth this relates to your work, This is basically answering the question of how come it's okay X-ray techs get this radiation exposure that's much higher than the 50 times what the U.S. public is exposed to. How come that's okay, right? Well, it has to do with population sizes. The U.S. public, as a population, has a dose limit of 1 millisievert. Us as X-ray techs have a dose limit of 50 millisieverts, but we're a much smaller population, right? There's maybe 50,000 people employed as X-ray techs actively, and I don't know what NucMed would add to that, but overall, it's a fairly controlled population. Let's just guess that 75,000 people work actively in medical imaging or around nuclear power plants in the United States of America. That's a very small population. The number of those people who also chose to work in that population and then marry someone who also works within that population is that much smaller, right? So the likelihood of there being some kind of genetically inherited trait that these two people working within this population could pass on to subsequent generations is decreased. We're basically spreading the love around, is what the scientists are telling us. That we're going to control population sizes, and that's going to be part of how we control dose limits. It's kind of cold-blooded when you think about it, but that's the way we have to think about this thing sometimes. The other way that this is used is in NCRP report number 160. This is how these numbers were arrived at. Is they calculated collective effective doses off of U.S. Census data and moved large data sets and crunched a whole lot of numbers to come up with these approximates, right? And the way that they did that was they did collective effective doses for the entire U.S. population for all these different kinds of exposures. And they averaged that all together and they gave us this nice, neat little pie chart that's easy for me to understand, right? And it's easy for me to make policy. You can give this to a politician and they can clearly understand things about how policy should be written related to this, right? I don't have to get lost in the weeds. So just two more kinds of units that we need to talk about. The TEDI is defined by the NRC to monitor and control human exposure to ionizing radiation. It's a total effective dose equivalent. And with this amount we can, so this is the total effective dose equivalent for the person. It's the closest thing to like a whole body dose statement that we could make. So when we made that effective dose statement earlier, I just said here's the effective dose for the lungs, right? This is saying an effective dose for the entire body, right? And as you can imagine, this is very, very difficult to calculate. We will not be calculating this. People use simulators and things like that to calculate this. But we do need to understand what a TEDI is. And related to it, the CEDE, do y'all call it something else in NucMed? I've heard some folks call it a SETI. This is a committed effective dose equivalent. And this is, when we talk about committed, we're saying, say you inhaled or you ingested some kind of radioisotope. If it's not excreted from your system, your body is committed to receive the total dose that that radioisotope gives you through all of its various decay processes, right? So I looked real closely at what's the cutoff for that, because some of these radioisotopes might have half-lives of thousands of years, right? It's over 50 years within your body. So again, this is just to emphasize again, don't use the PET-CT bathroom, right? Because the stuff that is in there, if it gets in your body, you're like, it's fine, use it anyways. There's not a line there. If it gets into your body, though, your body's committed to receive that entire dose. You tracking with me? It's going to be a gradual thing. But that's what that unit is. It gives us the ability to talk about. So the TEDI is designed to take into account all possible sources of radiation exposure. It's useful for dose monitoring for occupationally exposed personnel such as nuke med techs and interventional rads who are likely to receive a possible significant radiation dose during the course of a year. And here's just some stuff for your information. Don't worry about this down here. I'm not necessarily interested in y'all figuring out how many ergs are in a joule or any of that kind of stuff. I honestly don't even know. Alright, and there is a YouTube video out there. You're welcome to look it up on your own time, but it is someone measuring the amount of radiation that a banana gives off, and it's pretty shocking. I almost wonder if they've like treated the banana with something. But yeah, check that out if you want.